In this video, I will explain the different solution methods in Fluent. And from solution methods, you can go from the solution and double click on the methods. And here we have the coupled scheme. And second is the secondary solver, which means that we solve the continuity equation and the momentum equation in a sequence. So there will be one matrix for the at a time for the each variable. And from the solution of continuity equation and momentum equation, we get the pressure field and velocity field. And if you're solving the three-dimensional flow, then you will get the three components for the velocity x, y, z. And difference between this coupled solver, which is here, and when you solve the density based, which is also a coupled solver if you are running as implicit, that in the density based coupled solver or implicit solver, this will solve the three equations in a one go. That is the continuity, momentum, and the energy equation. Energy equation for the temperature field, and then we get the variation of density from the equation of state, and also we can solve the viscosity if it's a temperature dependent, and then the other variables, they can be the chemical variables like a concentration factor, or the turbulence variables like for the k omega, the k and omega are the turbulence variables. They will be solved in the sequence. So there are three methods. One is segregated, that is the simple, simplex, and the piezo. In these methods, in these three methods, all equations will be solved in a sequence. So first continuity, then momentum, then again the solution will be as an input for the from velocity field, as an input for the continuity equation we get the pressure field. And although you will say that the continuity equation does not contain any pressure term, but if you modify that equation, you can get them in terms of the pressure. So anyhow, so we solve them in a sequence, and then we go for the energy equation if there's some temperature, like for example we are solving the flow in a room. In that case, you can uncouple these equations. You can go in the sequence. But the problem is that with simple, simplex, and piezo, because the equation uncoupled, so to get the convergence or to get the convergence of pressure and the velocity field requires a lot of iterations. But benefit is that it will require the half resources. So the rule of thumb is what I learned from my learning here is that for the 1 million nodes, you need around for 1 million nodes you will need that is cells. So you need 1 GB RAM in terms of the simple, simplex, and piezo. And for the coupled solver, you would require for 1 million nodes you require almost at least you require 1.5 GB to the 2 GB. And for density based solver, you will need the 4 GB for the 1 million cells. So this is how you will see how the problem will require the computer resources. So in the simple 1 GB for 1 million, in coupled pressure based solver you will need the 1.5 to the 2 GB for the 1 million nodes, and in density based solver you need almost equal to the 4 GB for the 1 million nodes. So here this video will only concentrate right now on the next video will be comparing the simple and the coupled solver, or simplex and the coupled solver. But right now we are going to see the coupled solver, which is default solver option in the Fluent right now to solve the equations in the iterative fashion for the momentum, continuity, and other equations. So if we double click on the run calculation, we get some parameters here. So I will keep everything as it is in default form. I will just play with the time scale factor. So first I will play as the default value of 1, and then I change this value after few iterations in the second case, which is same will be shown in the same video. So I will gradually increase from the 1 to the 10, then after 10 to 20 iterations to 20, then 30, and you can go up to the 50, but I will just be limiting myself to the 30 time scale factor. So I will tell you the difference in the results, the convergence pattern, and the number of iterations required for the convergence with these factors. So after going through this problem, which is basically on the wind turbine, but this will be the knowledge you can apply on any problem. So right now everything is in the default setting, so I will click on the calculate. And before that, I want to define the report definition. So all variables are defined already there. So I will click on calculate, and basically I am monitoring the momentum or the torque value on the blade. So there are two graphs. One is for the momentum coefficient, and that is not the proper representation of the momentum or the torque value. And second is the torque itself, which is in the newtons meter. And right now you can see the performance, and almost all of my memory is being used for the Fluent. But if I check the respective Fluent operations here, so it's around 6.2. So I can multiply 6 by the 424 and then 1 GB in terms of these MBs. So 25 GB I'm using for this problem, which has around 14.7 million cells. 14.8 million cells. So it's approximately, if I use a calculator, so 25 divided by 14.8. So it's almost 1.7 factor. So it means that for the 1 million nodes, 1 million cells for the tetra mesh or with the mixed cells, we count the cells. And in terms of hexameshing, even we are with the cells, because this is what the Fluent is solving. But in the case of hexameshing, the number of cells and number of nodes are almost equal. But in the case of tetra mesh, the number of cells are almost 4 to 5 times of the number of nodes. So this is the one of the disadvantage of the tetra mesh, that it will contain around 5 times more cells as compared to hexameshing for the same number of nodes. So we are getting solution on those nodes, but we are solving the more cells, and it means that it will require the 5 times more resources compared to the hexameshing. Maybe for some cases you need the factor maybe the 1 to 4 for the 1 million nodes. We have the 4 million cells, but the ratio will be 4 to 5. This is the advantage of the hexameshing. And so right now we are at the factor for the 1.68 or 1.7. And now it will start to solve the case, and I will wait for the solution to converge from this point onward. And right now this is the CM value, or the coefficient momentum value, and here is the moment value, which is basically the torque on the along the shaft, along the z-axis, which is the axis of rotation. So I will wait for this solution to converge, and in my calculation, what I observed here is that it may require 8 to 900 iterations to solve this problem completely. Whereas if I change the time scale factor to the 30, it may require 150 to 180 iterations. So I will show you on the screen everything, each and everything one by one. And if you take a look on this solution that we ran yesterday, and almost 24 hours, and so for these 14.8 million cells with my i5 processor and 32 GB RAM, you can see that for the last 24 hours we are only able to solve the 652 iterations, and the solution was, first it was increasing, and then it is decreasing at a very slow pace. And you can see that in the second digit, the solution is after the decimal place, so solution is changing. So it is 3.8716, which is 387.38716, and 38710, 38705. So now it is decreasing at a very, very, very slow pace. But on the other hand, if you go for this is the plot, basically we are talking about, the first one was the coefficient momentum, and the reference values are not correct for this purpose, which is for wind turbine. And this is the graph we are talking about, which the values which are decreasing to the, in fact this is the graph over here. So this is 387, and right now it's less than 400. So I will wait for this solution to complete, and it will take around maybe 1000 iterations, and then I will change the time scale factor with a new solution, with a new simulation to the 30. I will run the solution with the time scale factor 1 for the first 10 iterations, and then again I will change the value to 10 for 5 to 10 iterations, and then 20, and then 30. So I will ramp up the solution from the time scale factor 1 to the 10, 20, 30. I will not go beyond the 50 or the 30 value, 50 or 100. So, but you can go after even after that value. So what I've seen that the solution is not converging very fast with the higher value for time scale factor, and secondly the solution has no difference with the 30 or 50 in terms of the values of the variables or in terms of the solution convergence rate. So that's why I usually use the 30 value. Although we can stop solution here and increase time scale factor by a little factor, let's say to the 5, but the point is not here the convergence. Point is that we want to compare the time scale factor 1, which is default value, to the value which is like 30. So that's why I will let this solution to run to the next 400 iterations, like maybe up to 1000, and after that I will stop solution. Alright, so I will stop the solution at this point. And as you can see that the solution is converging at a very slow pace. And the value I got after like 1000 or more iterations, around 365, 367. But I think this running this case for the longer time will be a waste of resources. So I will stop solution here. And now I will show you that if you change the value to the 30, so what will happen. So first of all, let me save this file. So I will save both case and data files. And again I will make the solution initialize from the scratch. So from inlet boundary condition. And you can also use the hybrid initialization. So hybrid initialization is basically uses differential equation to get some rough solution on the domain. But right now I'm going to use this method, which is the old method in the Fluent. Okay, so this case was running from the 6 a.m. and now time is around 12 noon. So you can see that it has solved the 493 iterations. And if you take a look on the graph for the moment, which is the torque value basically for the wind turbine, you can see that the value was converged between 50 and the 100 iterations. So to be on safe side, I would say, okay, I would suggest that we take the 100 as a starting point for the convergence, and then the solution remains same. That is the fall all the iterations over here. So it means that as compared to the previous case where we had the time scale factor is equal to 1, for this case we can get the convergence of residuals. They are also reaching to the lowest values. Previously it was -2, now it is -4. And this is also achieved within up to the 350 iterations. And but for the variable of interest, which is torque here, it was achieved between the 50 and 100, or you can say 75 and 100, and onwards it is constant value. It means that if you use the coupled solver as the time scale factor is equal to 30 or more, or maybe 20, you can get the faster conversion as compared to when the value is set to the 1. But depending now, it depends on the your mesh and everything. So if you have the problem with the mesh, or the solution is not converging with the high value of time scale factor, so in that case you have to go back to the 1, and then you have to wait for the solution to be finished within the required number of iterations. And second thing you can observe here is that the value of torque is 3.67 to the power plus 2. It means the power is 367, but in the previous case it was around 380, and it would have taken like maybe 2 days to reach this value. So that's why I would recommend that if your mesh is of very high quality and you don't see any conversion problem, then you should set the time scale factor to the maximum possible value. So from this video, we can conclude that whenever you want to run the couple solver, pressure-based couple solver, so you should consider changing the timescale factor. And second thing you can change is you can specify user specified timescale, which is pseudo time step, and you can also play with this time step, and you can get the better convergence. But right now, these are the default settings, and I just changed the value from 1 to 30, and this is what I got from in terms of the convergence.